radio frequency and the free space optical communication system and the importance and applications in future wireless communication systems. This system increases data rate and link availability with diversity advantage by uniting both communication channels at radio and optical frequencies. It will be widely used in future wireless communication systems, including key areas such as satellite communication. The hybrid, the IFO and the FSO communication system has potential benefits in terms of channel capacity and system robustness. For example, by combining radio frequency and free space optical communication, the system can flexibly choose the best communication method under different environmental conditions, providing more reliable and robust communication links. However, we must always be aware that its performance is affected by natural phenomena such as weather. For example, when it rains, channel attenuation causes the received signal power to drop. Our project will focus on the frequency of weather effects on channel attenuation. Our project aims at modeling channel attenuation for hybrid RF and FSO communication systems. We will provide data including RF and FSO channel attenuation data as well as weather parameters such as temperature, humidity, and visibility. The figures were generated based on real-world empirical data obtained from hybrid systems operating in 6 cities around the world. It is worth mentioning that the value of the snap code represents the value of the weather conditions. For example, when the snap code is 8, it means it is snowy, and when the snap code is 4, it means it is sunny day. When we process the data, we need to convert this variable into a categorical variable. 3 models will be used in this project. They are linear regression model with interaction term, and random forest. While height is the estimated value of the response variable, while I is the value of the response variable, y bar is the mean of the response variable. R squared is a statistical measure used to evaluate the effect of a regression model. It represents the proportion of the variance of the independent variable that can be explained by the model. That is the ability of the model to expand the data. The value of R squared ranges from 0 to 1, where 0 means that the model fails to explain the variability of the independent variable, and 1 means the model fully explains the variability of the dependent variable. A higher R squared value is consisted to indicate the better fit of the model to the data. It should be noted that R squared is not an absolute indicator. It has its limitations. For example, R squared can overestimate the performance of a model when it overfits the data. Therefore, RMSE is also used in this project. Unlike R squared, RMSE is an absolute measure that provides a measure of actual error, not just the explanatory power of the predicted value. A small RMSE value indicates that the prediction error of the model is small. That is, the prediction of the model is close to the actual observation. Y is a dependent variable. X1, X2, blah, 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 and XP are the independent variables. Bet 0, bet 1, bet 2, blah, 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 and bet P are the coefficients of the model. In the 2 data sets of FSO and RFL, are the respective used as dependent variables, and the rest of variables are used as independent variables for research. In the linear model, in the FSO data, and the number of terms is 15. In RFL data, the number of terms is 11. This is very simple. Now I'm going to focus on introducing linear regression model with interaction. X1 times is X1, X1 times is X2, XP times is XP. This process will generate about 200 new terms. We will need to drop some important terms. So question, why drop some important terms? So the first reason, because of reducing overfitting. When a model contains too many irrelevant features, the model will overfit the training data, resulting in poor performance on unseen data. The second reason is that by discarding unimportant terms, the dimensionality of the feature space can be reduced, speeding up the training. The third reason is that some features may contain noise or useless information, which may affect with the linear process of the model. As can be seen from the first figure, when the number of terms increases from 0 to 50, the value of RMSE decreases rapidly. When the number of terms increases from 50 to 100, the value of RMSE decreases slowly. When the number of terms increases from 100, and this curve flattens. As can be seen from the second figure, when the number of terms increases from 0 to 50, the value of R squared rises rapidly. When the number of terms increases from 50 to 100, the value of R squared rises slowly. When the number of terms curve flattening of R squared as it increases from 100 to 200. In Figure 3, when the number of terms increases from 0 to 15, the number of variance of coefficient times the feature decreases. When the number of terms increases from 15 to 50, the value of variance of coefficient times feature is still dropping. This is because the range of variance of coefficient times feature is from 0 to 13 surrenders. From those four fingers, we can conclude that when the number of terms in the model is 50, the performance of efficiency of the model are better. The FSO data is processed in a similar way to the RFL data, so I won't discuss it too much. The 25 terms will be saved in the model. Okay, then Forest can get more accurate predictions by combining the result of multiple decision tree, ability to handle missing values and unbalanced data. For feature importance ranking in decision trees, it can provide useful feature selection information. The process of decision tree construction is to build a decision tree model independently for each training subset. In Figure 7, during the construction of the decision tree, for each node, a part of feature is randomly selected for evaluation, and the best feature is selected as the split criterion. This random feature selection method helps to reduce the coefficient between features and improve the diversity of the model. From Figure 8, we can see that when the minimal node size is 2 and the number of randomly selected predicted is 3, the random forest performs best on the RFL dataset. From figure 9, we can see when the minimal node size is 2 and the number of randomly selected predicted is 4, the random forest performs best in the FSO dataset. This is about a comparison between model performance. We can find that the linear regression model with interaction performance is better than linear regression model performance. The RMSE decreases in the test set, and the value of R² increases in the test set. However, we can still find that although the linear regression model with interaction performance is better than linear regression model performance, the value of R² is still large, and the value of R² is indeed small. This may be because linear models usually only capture linear relationships in the data. For data containing nonlinear relationships, linear models may not fit the data well, resulting in poor model performance. In the method using random forest, the value of RMS on the test set is small and the value of R² is close to 1. Among those 3 models, random forest is the best performing model. From figure 11 and figure 12, the blue curve represents the predicted curve, and the black curve represents the real value curve. We can see that the predicted curve is very close to the real curve. This shows that the random forest method has better generalization ability and robustness in RFL and FSO datasets. Okay, let's go back to figure 11 and figure 12. In figure 11, we can see that when the value of x-axis is greater than 30, the predicted curve and the curve of their value deviate. In figure 12, we can see that when the value of the x-axis is greater than 20, the predicted curve and the real value is biased. This may be due to the lack of RFL data greater than 30 and FSO data greater than 20, resulting in insufficient data fitting for the model. So my suggestion is to collect more RFL data greater than 30 and FSO data is greater than 20. In addition, we can further improve the performance of the model through ensemble learning technology. Those technologies can further improve model accuracy and generalization by building an ensemble of multiple models. Okay, that's all. Thank you for listening. If you have any questions, please contact me. Thank you.